think we'll continue the discussion on that. Okay. So our next speaker is Don Marshall. Actually, I'm kind of silly. I don't really need to talk about Don Marshall. I know him well enough otherwise. I did check on a few things. He got his PhD with John Garnett at UCLA in 1976. I didn't know this before, but won a prize for best thesis, science thesis at UCLA. Congratulations. Before that, he'd worked in many years in industry at the Jet Propulsion Laboratory for Aerospace Corporation, so that explains why he knows a bunch of the numerical things as well, I suspect. His early work was on something called the Cheng-Marshall theorem, which, since it's named after him, and has a name at all, I don't think any of my theorems are called Bishop theorem. It's a pretty important theorem. It's about the algebra of analytic functions on Unix, bounded analytic functions. That's a special subalgebra of all measurable L infinity functions on the circle. There's a subalgebra of the ones that extend to be holomorphic on the inside. And Don and Alice Cheng characterize all such algebras. They're called Douglas algebras, with Stony Brook connections, since Douglas was here for a long time. And in fact, although he doesn't work in that area anymore, there's a lot of activity in function algebra type things, and almost all of it is devoted to try to come up with something as good as the Cheng-Marshall theorem in other settings. And not much of which has been very successful, and nothing has been that good. Since then, he's done a lot of work in harmonic measures, conformal mappings. There's one particular example involving the best constant in Hall's lemma, where he was led by numerical experiments to what the answer was, and then give a rigorous mathematical proof of that. And it's a very pretty thing, which looks like this. Recently, he and John Garnett came out with the book Harmonic Measure, everything you want to know about geometric function theory, 300 or 400 pages or less. I consider it, the standard reference now. As I mentioned in my review of it, I have a lot of books on my shelf. I have 3 or 4 books I actually keep on my desk, and this is one of them. And so not just because my name is mentioned on the back cover. I'd like to point out. Very important.
You keep it upside down.
Yeah, well, so I can read it. Yeah. Well, I read the most important parts. But I encourage you to buy it and to use it. And if you want to know things about outforce distortion or extremal length, the whole beginning of the book is all the basics, and the latter half of the book is what's exciting happening in the last 20 years, and up to really just the last year or two. So, Don, please take it away. We'd be very happy to hear what you have to say today.
A lot of the end of that is really first.
One thing I left out was Don's also the author of the software Zipper for doing conformal mappings, which I think we're going to hear something about today.
So I begin with an apology that I'm not a numerical analyst, and so I'm liable to say some rather naive things. So please educate me after this. That's the case. So what I thought I would do is first say why I got into this numerical conformal mapping, where the problem came from. I have a slightly different perspective, I guess. And Chris talked about the maps that are approximately conformal to the exact region. My example, I want to be exactly conformal to the approximate region. And the reason comes from the first place that I started using this stuff. I was at the Lepler Institute in 1983, and Carlson and I were working on certain extremal problems for univalent functions. So phi is a conformal map to simply connected domain, and it was known for these kinds of problems that the extremal function was a map to the complement of a curve that headed off towards infinity. So in order to try to make these supremum big, we transferred the problem to the curve. D theta transfers to the d omega harmonic measure on the curve itself and changes your kernel a little bit, but the function phi now is an identity function. And by looking at it,
d omega? D omega?
Harmonic measure. The transplant of d theta to there's actually 2 sides to the curve is the way to think of it. If you think instead of the disk, you look at the half plane, and as we've seen in a couple of talks already, you fold the line around to itself, and with some stretching and compression, and that gives a curve. And it gives a natural identification of points on the left and right-hand side of the origin. X and h of x are mapped to z. So the idea was basically to try to build the kernels K were highly oscillatory. And so we would want to build a curve that has harmonic measure oscillating roughly like the way in which the kernel is oscillating to make this interval figure. I can say more about that right here. It's just the idea that we can
work with an example of why you do this for a second.
What this kernel is, or
yeah,
what's the motivation for the disagreement problem?
So K might be cosine 2 pi n theta, and you're computing the nth coefficient of a univalent map. You want to know how big that coefficient would be at the time the Lieberbach conjecture is not solved. Boundary area has come by and had a bunch of polynomial problems, which looked real good for low degrees, and then for higher degrees somehow fell apart, and he suggested that the Lieberbach conjecture was to fail. It ought to fail for coefficients around 17. There should be odd coefficients in around 17 to 19. And so we were trying to understand what could possibly go wrong there. So you have something that's oscillating really rapidly on the circle, and you want to somehow build examples and curve, make the interval much better than, say, the straight line. Overall univalent functions normalized. So first, of course, you try to do what you can by hand, and essentially the only example that you can work out is a map to the complement of a curve that has a single bend in it, and you can write down the formula for that explicitly. But in terms of our kernels, actually, it turned out that near this bend, you actually get a little bit of an improvement beyond the linear case. The difficulty was that as you went out to infinity, you paid a penalty because of the line at that point. So what's needed is more bends to your curve, and so we asked around, and Henrici told us that about Nick Trepethan's nice, fairly new program on Schwarz-Christoffel at the time. And so there, we tried to apply that in this case here. So you think of your curve as a collection of points, or maybe the intervals. In this case, you could take them as straight line segments. Each such arc, AJ, comes from two intervals on the real line, one on each side. They're mapped to the two sides. So basically, harmonic measure is dx of 1 plus x squared, say, on the real line. So what you'd like to do is specify the intervals on the real line and construct a curve that identifies those intervals. We don't care too much about the shape of the curve. What we care is that it has the right behavior of harmonic measure on each side. Well, unfortunately, the Schwarz-Christoffel at the time could only do about curves with about 20 bends or so, and that doesn't help much. I mean, it came pretty close, but it didn't quite help us understand what was going on with cosine 19. So when I returned to Seattle the following June, I realized that the map that we could write down could be used in a different way to solve this problem with lots of bends, although they're not straight lines. So here is the map.
Should be a different one somewhere around here.
So we're going to map the upper half plane to the upper half plane minus this slip. And here's the formula for it. And you can see that A and A minus 1 are both being mapped into the origin, and you can compute that the origin is mapped to the tip of the slit. And the slit is at an angle pi times A. So what happens is these two red intervals are pushed together to form a slit. The two blue intervals, the rest of the axis outside of it moves in towards the origin. And so this is basically the square root of that first map. So the idea is that at this stage we've identified the two red intervals, if we compose two such functions, then the red intervals still stay identified. So in other words, the main thing here about this map is that the total length of red there is 1. So if we look at the next two image blue intervals here and rescale it by a constant c, it'll now have length 1. And that gives us a number b, and we apply the same map with the parameter b to get another slit with a different angle. The image of the first slit here is no longer a straight line, but basically if these lines go up, then this is going to be not too far from a straight line between the two data points. Now the next green intervals move into the origin here at this stage, and you just do it again. So suddenly now we can do 10,000 little tiny intervals, which means that we can basically ahead of time say what harmonic measure it is, and then compute. So to give an idea, just to take an example that one knows about, so this map, h of x is sometimes called the Welding map, although I don't think we knew that name at the time. But so here's an example where you use the Welding function x to the 1/3, and it gives the map is exactly what you would expect. On one side you have square root z, on the other side you have z to the 3/2. The inverse of z to the 3/2 is z to the 2/3, and z to the 1/2 is z to the 3/3. And just to give a picture of what the accuracy looks like, here's 200, and if you divide by 10 to the 4, it's very much like there's been a lot of work recently on the connections between conformal mapping and probability problems from statistical mechanics called stochastic Lerner evolution. And they generate basically random curves in the upper half plane, and what they call now the standard method comes exactly from this composition of these slit maps. And so here's a program written by my colleague Stefan Rode to simulate SLE. So basically what you see at the bottom there is a slit with angle pi times a and its complement pi minus a. And you randomly choose which one of those at each stage. Okay? And that creates a curve. It's renormalized at infinity, so it's not running off to infinity with the normalization normal use, but you can write down a connection between the so-called kappa parameter in SLE. This one was kappa 4, and you get different kinds of random curves. The higher kappa is, the more the curve comes around and then the limit touches itself. It's been used to solve a number of problems in conformal field. And it's very rapid to compute these curves, as you can see here. Most of the time it's taken when you draw a curve, you have to erase it by drawing on top of it again, and then you draw the next one.
It's sort of the same on both sides.
What's the you have this random choice of A and
Yeah,
pi.
the structure looks sort of the same on both sides.
In a sense, yeah, because you roughly half of the time go one way, half of the time go. Oops.
At least shows a different parameter.
Robots will take over.
Right in the way of the five.
Can you just say again what you said? What's randomized on the
So
A?
I'm going to take two
So you have
maps.
these maps.
One map, I'm going to fix an A.
Oh, so
Take
that's
one
really the
map with
proportion
angle
on one
pi
side.
A, and the other map with pi minus pi A, and randomly choose which ones. And there's a formula between the kappa and
So I think one of the most recent Fields medals was given for coming up with this and developing this theory.
yes, the connection between Lerner's equations by Oded Schramm and Oded together with Bellman Lerner all developed the connection for solving physics problems, for example, the dimension of the grounding functions using this technique with a particular value. Okay, So the context that we saw here was just a little bit different. Instead of a curve, you have a map from the disk to, say, a Jordan domain, both the map from the inside and the outside, and the identification is similar. It's given by this Jordan domain, so these maps extend continuously up to the boundary. Homeomorphisms, and so the composition of one with the inverse of the other is an increasing homeomorphism of the circle. And if you normalize it so that it, say, sends one to the same point, the mapping will, that gives you a mapping from 0 to pi itself, which I think David told me, I think there's a program right now down at UCLA in random curves and random surfaces, and someone from down there asked me to run some examples of random weldings. So this was the best I could do in a day to try to figure out roughly a random quasi-symmetric welding. The idea is that it isn't exactly quasi-symmetric. You take the interval, 0 to 2 pi, you choose a fraction ahead of time, 0.4. And you divide it into two intervals, one 0.4 times the length and the other 0.6 times the length. And then you take each one of the two remaining intervals and divide them 0.4 and 0.6. But at each stage you randomly choose which side gets 0.4 and which side gets 0.6. And so I used a program of Blue to generate random numbers, and the red curve, so I generated one sequence of random numbers and applied it with 0.4 to get the red curve, and then 0.3 and 0.2 for the remaining two curves. Corresponding.
So instead of when suppose you were given a tab of voices ahead of time, given by some kind of just log, I guess, or something. Did you try that?
Oh yeah. I mean that's all it is. Once I've randomly assigned it, now I've got a specific sequence. I have a specific map, and then from a specific map you construct. Another one, the enemy with these weldings is slope 0 and slope infinity. You keep your slopes away from 0 and infinity, then you have a nice quasi-symmetric mapping, and you know that the image is going to be a quasi-circle. So here, well actually, the best way to sample this is, and Stevenson pointed out, is along a line of slope 1 to rotate things down. And then you have a map that has slope between plus and minus 1. And so this is not, you can't have horizontal line segments and increasing homeomorphism, so it's slope 1 minus epsilon and slope minus 1 plus epsilon. And randomly chose to make it hit 2 pi at the end, and expect it to hit 2 pi at the end. Large probability to get close to that. So what I did was just flip it halfway through to make sure that you got the full distance, and then create the curve. This is what you get. And it's sort of interesting that you know, this is roughly flat on large scales, and this is roughly around on smaller scales. But it looks, you know, it looks like one of these rivers I saw on the flying over here. They're roughly straight, but it wanders a lot. Huh? Yeah. And the wandering comes from the fact that you want to have a very small slope. Means that it's very easy to get to the curve from one side compared to the difficulty to get from the other side. And that's what these little channels are. It's much easier to hit this. You see that? It's much easier to hit the this bump from this side than it is to get through the channel. And then the program is fast enough that if you have, say, some homotopy of your curve, you could take a homotopy of your welding. I just did a simple-minded homotopy here. You just get a sequence of curves when you do the welding, and so this is a way to continuously deform the curve into a circle. So there's a couple of issues here, which I guess may have been pointed out already. If you're in the smooth category, you have the welding map and its inverse both smooth, and if you suitably normalize the welding maps and normalize your curves with respect to the base point and maybe infinity, then there's a nice one-to-one correspondence between curves and welding maps.
The smoothest level is exactly zero.
Not at the integers. So in other words, if you take a curve that's C1 plus alpha, then the conformal mapping is also C1 plus alpha, alpha strictly between 0 and 1, and the same for both the inside and the outside. So if it were right at C1, then you lose. But another difficulty that occurs is that you can have two very different curves that correspond to exactly the same welding, either outside and smooth class. I think Chris was probably the first to point out that these curves have to be really nasty, essentially positive areas. They're not the kinds of shapes that you run into in practice. There's also another problem, which is, and I think Chris again was one of the first to point this out, that there are weldings which don't correspond to any curve. The welding itself can be smooth. If you don't require also the inverse to be smooth, then the object that you get is not a welding. Here's a simple linear map. So when you're doing these things numerically, you have to be careful of the technique that you use in order to compute the map from the welding. If your welding is simply piecewise linear like this, so there's a bend at pi and also a bend at 2 pi, when you look at the curve, you get these two crinkles corresponding to 0 and 2 pi, and if you start zooming in on those crinkles, they turn. In fact, you get an infinite spiral, which that one bend. Another source of difficulty is the following. And here's a curve that's symmetric under 40 rotations, 2 pi over 40. And if you look at the conformal map, say from the disk to the inside region, it sends the origin to the origin, and say 1 to 1. And then by the uniqueness portion of the Riemann mapping theorem, you're going to have an invariance in your mapping function under the same 40 rotations. In other words, the 40 equally spaced points at the very tip will be mapped to 40 equally spaced points on the unit circle. The same thing happens for the map from the complement to the complement of the disk.
So the power series only uses multiples of 40?
Yeah. You could apply z to the 40th to this, and you would get a simply connected domain. And then the real map is f of z to the 40th to the 140th. But the point simply is that if you take the map from the inside to the disk and the outside to the disk and compose the inverse with one and the other, it'll be the identity on these 40 points outside and also the identity on the 40 points inside. So if you tried to draw the welding, you would get these 80 points where it's the identity and it has to be an increasing function, and so you can't tell the difference. So how you treat the welding in between the vertices is really important. Your curves could oscillate rather dramatically like that. Now, I wanted to describe a simple modification because it's easier to prove things about it. It also goes a lot faster, and the inverse is also easier to write down. I'm going to do this on the right half plane instead of the upper half plane because I keep getting emails from engineers and other people who try to write out their code and they have difficulty with the branch cuts. Okay? So when you take a square root in most languages, the cut is along the negative reals, not 0 to 2 pi. And this is the way to handle it on the right, is to use the right half plane. I'll say more about that. So what we have here is two red intervals on the imaginary axis, so 3 points, and we map that by a simple linear fractional transformation of the right half plane to itself that sends those points to -I, 0, and I. Now we apply the map z squared, which folds the axis down onto itself, identifying the two red intervals, which we wanted to do. We slide it over so that it goes out to the point 1, and then take the square root, and we have this very simple map. So we want to use that instead of these maps that have angles in them. Of course, what would happen is if you compose two of these at the next stage, you would apply a linear fractional transformation so that interval from 0 to 1 now becomes an arc of an orthogonal circle, and and then you push it out again with another one of these methods. And the inverses of these maps are very easy to make. So here's the idea to do your welding. I'll think of my welding now as negative imaginary and positive imaginary. You push out the two red intervals around the origin here to an interval here. In the process, maybe this is not like Toby's picture, drawn precisely. This is a freehand. The positive axis is first mapped to an arc of an orthogonal circle by the linear fractional transformation, and then square root of z squared plus 1 pushes it out to some other curve, maybe something like this. And now the two green intervals are adjacent to each other. You apply a linear fractional transformation. This point here might have gone around the negative axis or something like that. But you continue pushing these out until you've identified all of the intervals except at the very end, where you have an interval from 0 to IT. IT is always the trace where this point goes. And so the last interval is a brown interval here, and a brown interval from 0 up to infinity, and then around.
So IT, that point is infinity in the very first picture?
It's infinity in the very first picture. And so you send it to infinity now with this linear fractional transformation inside here and square it, and you fold the blue two brown intervals. First make it two half lines by the linear fractional transformation, and you apply z squared to fold them together. And so then you get this curve that has exactly the identification you wanted. And if you go back initially and just cut the plane along the positive axis, you can see that this quarter plane is mapped to this half plane. And the other quarter plane is mapped to the lower half plane. If you want a bounded region, apply a linear fractional transformation. So quarter planes are the same as the distance complement. So this gives a map from the distance complement to a region. Furthermore, these steps are reversible. Every one of these maps has a very simple inverse. If you started out with a domain and you wanted to compute the welding, you just do it in reverse. You choose 2 points, say z1 and z2, send 1 to 0 and 1 to infinity, and then the rest of the curve would go out to infinity. You look at the next data point here, and, well, first you take a square root. So it looks like this, and the curve runs out like that, and what you have now is a point here 0, and a point, instead of being 1, is at some point which is not quite 1. So you take a linear fractional transformation that fixes the axis at 0 and sends that new point to 1, and then you take z squared minus 1 square root to open it back up. And you continue opening this thing, unzipping it. Sort of like grabbing the axis here and here and pulling apart the zipper right at that point. However, not much was done with this because we couldn't prove that this converges. Everyone knows that iteration of very simple functions in complex dynamics gives really nasty results. But
This is square root iteration, sort of, right?
yeah, it has that in there too. But what the key thing back here is to look at this map. You actually get to erase these blue lines here by Short's reflection. This is a map from the complement of that line segment to the complement of this line segment and its reflection. And outside of, say, a disk right there, you have a nice power series expansion about infinity. In fact, once you move a little bit away from this interval here, the map looks very much like the identity, or linear fractional transformation. So what you're really doing, instead of sending points off to infinity, you can think of this as little small changes along your curve, and each of those small changes is only affecting the curve locally. So you start flattening out your curve a little bit at a time. And so all of the effects a little bit away from these small little bends is very linear, and the errors will accumulate very linearly. So what we could prove for a long time was an a posteriori estimate. In other words, you run the conformal mapping program, you look at the parameters, all of these A's here turn out to be very close to 1, and all of the B's turn out to be very close to 0 every time you run the program, except when you make very sharp bends. We'll talk about bends later. And you can prove that if the coefficients A and B, those parameters are all in a certain region, you can then use the size of that region to give a uniform estimate on how close your mapping function is. As you say, started out with a bunch of data points around the boundary, you can estimate how far the curve is from the line. But if we wanted something a priori, something that we could say ahead of time, how close it would be, how do you distribute the data points, and some geometric notion of how badly this curve is oscillating between them. So recently, together with Stefan Rota, proved the following simple result. I've stated it for C1 curves, but there's many other versions for it here. So the idea is if you take a C1 curve and just distribute points around the boundary with a small mesh size, then the mapping functions, as the mesh size goes to 0, the mapping functions will, if you do it, say, on the disk, will converge uniformly on the closed disk. Both the inside and the outside mapping. Furthermore, this curve that you construct is actually a C1 curve. In fact, it's C3 halves. So, in fact, the unit tangent vectors will also converge. So, in the C1 sense, you converge to the C1 curve. Also, the welding maps converge uniformly to the welding map for the curve. You can prove, you can give a constructive proof of the Riemann mapping using this algorithm. I'm not using the Riemann mapping. For Wilder curves, here's one possible version. I actually think that quasi-circles or quasi-symmetric welding is the right domain for these kind of maps. You don't want these linear fractional transformations to send the point 1 to a point down near the axis. It's not very close to the curve going up. So if you start out with a K quasi-circle with some control on the quasi-conformal constant and choose data points. Now you have to be careful. You can't just randomly choose points because a quasi-circle can have a dense set of infinite spirals around the boundary. So if you just randomly chose a point and then another point might be back here and back here and back here. So you run into problems then in that way. The curve might not move in the right direction. But if you choose them roughly equally spaced, so the ratio between successive intervals is bounded above or below, then this process converges and produces a constant depending upon K, not on the domain quasi-circle. That does work. The proof first was hard, and now it's almost completely trivial. It's kind of embarrassing. But the idea is the following. To try to identify these points here are the data points. There's ZK and there's ZK plus 1. What is the curve that goes from ZK to ZK plus 1? Well, remember, as you push these intervals out, you identify them, and then they just remained identified from there on out. So how do you see what the image is of the curve? How do you get this curve from ZK to ZK plus 1? We can ignore everything that you did at the beginning until you get to the stage of constructing that interval, and you get at that point this straight line segment, which is an arc which is a geodesic arc in the half plane. And the images of geodesic arcs are geodesic arcs. So as you apply more conformal maps, it still remains a geodesic arc, hyperbolic geometry, the domain. And the domain at this point is just the complement of the curve constructed up to ZK. So if you take the complement of the curve constructed up to ZK, the next section of the curve is a geodesic in the hyperbolic geometry. And then we just use an old result of Jorgensen's, which says that disks are convex in the hyperbolic geometry. So if your curve goes from ZK to ZK plus 1 and enters this sort of lens-shaped region, the intersection of these two disks, it stays entirely within that lens-shaped region. If you take a C1 curve, for example, you can build these lenses that are with a fixed small angle by scaling down small enough and have the same tangents at each point. And so simply by induction, the curve then would go through this sequence.
So you have a better estimate of thinner lenses, which is the bigger two disks are. So how do you control the size of the disk?
This doesn't depend upon the scale. So in other words, if you have a C1 curve, when you go down to a very small scale, it's extremely flat. And so then relative to the spacing between the points, you can have big disks. I mean, they're tiny disks in the domain, but relative to the scale, they're big. And so that gives very flat.
So you could say, you write down some easy estimate in terms of the curvature of the boundary, as well as there's all these big tangent disks that are very flat.
You need a little more than the curvature of the boundary if you had a region that came back and folded back on itself like this. But it tells you what you need to do. You just need to, when this happens, you choose points that are closer together so that you can still build these disks down here.
All right, well, let's just say it's the minimum radius of the medial-axial disks. Use the word that everyone's taught.
So some of the advantages are it's a simple map. You use just very elementary maps. It's perfectly appropriate for first course in complex analysis. I've used it that way several times. Now the students, instead of just having powers and linear fractional transformations, can now build lots of conformal maps. It's that. Well, I said something about accuracy. That was just the proof. I mean, for a smooth curve, it actually is much more accurate than those lenses would indicate. Partly because if you had a control on the angle at the start of the map, the angle at the tip is only about half as big as the angle here. So it actually improves. But so for timing, it takes 10,000 boundary points takes 25 seconds to compute the parameters, which doesn't quite satisfy your 5-second rule. But let me make a quick argument that it almost does.
Well,
Because it does the following: it computes both the map to the inside and the map to the outside and their inverses all simultaneously. So that's 4 maps. So I can divide by 4 and then round off. Now, people have asked about the complexity. The complexity is O of n squared. If you imagine at each stage, you've got to move all of the boundary points. So you have to n squared. I'm not fond of this way of comparing different routines because n can mean something different and constant in front can mean something very different. You have a map to a domain and you use boundary points versus a algorithm uses interior points. Well, you're going to have about n squared interior points at the end points on the boundary, so it means something different. Or if you're using Schwarz-Christoffel, you have a bunch of vertices. You might count the number of vertices. For this program, you would have to put more points along the edges, and so the n would be higher there than the n for the Schwarz-Christoffel. If you have a smooth curve, you might have to use relatively more points for a polygonal approximation than you would with this smooth curve as to the data point. So n means something different. But what it is good for is estimating how fast this program is when you want to sit down at your laptop or desktop and run it. Because certainly in this regime here, down to about somewhere between 500 and 1,000 points, you can compute fairly accurately how long this is going to take by using this O of n. 5,000 points takes 1/4 this length of time, almost precisely. Good way to estimate. The other is that it always works. We don't have any convergence issues that we're worried about here. It always constructs a curve through the data point. The lenses were just to try to estimate, say for C1 curve or something like that, where the curve actually goes. But it always computes a conformal map to a region which goes through the data points. There's one slight exception to that, and that is if you create a curve between 2 points, and then a much later data point comes down and happens to land exactly on that curve, then you run into problems. If it misses the curve, it can still create a curve through the data point. And for the experiments, I mean, I use this for experimenting with univalent functions. It's important when you're doing an extremal problem to have candidates which are actually in the class that you want to investigate, particularly if they're delicate problems about boundary behavior. Because if it's not in the class you want, then you have to worry about how close it is to something. So, for example, Chris mentioned fast methods. A fast method of computing a map from the disk might be to use a fast Fourier transform. But if you take a univalent map and and you truncate its Fourier series, you're not necessarily going to get a uniform mapping. You're going to have spin at the boundary. So it cuts down on the kinds of problems I'm worried about. It cuts down on the worries that you have about the formal mapping that you construct. So it's always conformal. And you get uniform maps, not just uniform on compact sets. If you're really interested in boundary behavior, what happens near the boundary is very important to you to get uniform estimate. Also, the zipper version, that's the one with the bends in it, fits very well if you want to do, say, polygonal boundaries or boundaries with vertices, because it will put a bend exactly at those points. It does not handle non-Jordan domains. It's designed just for Jordan. The algorithm also well suited to Toby and Steve's beautiful idea of using cross ratios. Unfortunately, I started to program this up, and I sort of had a naive understanding of this. I felt that this program is really about ratios of successive intervals. And so I used simply ratios of successive intervals instead of cross ratios, which worked great most of the time until one of those linear fractional transformations said one of your data points are off to infinity, and then the cross rate. With successive ratios, if your middle point is very, very large, and that's okay, but when one of the endpoints is infinite, then you're in trouble. So I got to fix that part of this program, but there's no problem there. Here's some quick examples. If you do function theory on the disk, this is engraved in your blackboard from having drawn it in chalk so many times, it's sometimes called a Carlson engraving. Whitney decomposition of the disk where the size of each box is proportional to the distance to the boundary. I gave a talk at Canary Island, Tenerife, and so they got a volcano in the center, and this is what happens. What this picture is useful for example, is if you look at the previous slide here, if you look at a Brownian traveler that starts at the origin, he has equal probability of hitting each one of these boxes here. Likewise, if you go to a higher generation, an equal probability of hitting all of those boxes. So if you look at the domain here, you can estimate what's the probability that, say, Ash is going to hit out here, which is the beautiful beaches and seaside resort. And that whole tip there has the same probability of being hit as one of these little tiny guys way down here. But you still can't, even on this scale, you can't see the little tiny boxes from that state. So it's useful for estimating this compression expansion with this kind of picture. Incidentally, this is the boundary of Tenerife that I got off of something on the web, and I put a few data points between each because it's not a very smooth curve, and doing that, you can't see the difference between the computed boundary and the actual boundary, both of which are automatic. Here's a snowflake that a number of people have used for conformal mapping. Here's its Welding map. You can see that it's very singular at this stage, not actually not an approximation to the snowflake. It's not absolutely vertical. Highly horizontal and vertical, almost horizontal, almost vertical. So here I computed the map. What I've drawn there is the image of the boundary, which looks exactly like the approximating domain that I started with, and then took a simple homotopy to the identity. Choose your favorite homotopy from one curve to another, and use this to deform one curve to another. Ken Stevenson sent me a cat and an owl, so I changed one into the other, just using simple. It just goes, I mean, it goes very quickly. You can do these kinds of experiments. Perhaps a better homotopy might be to identify points maybe between years, or identify the years together, and construct your homotopy so that those points go together, and you can make one head move to the other head. And then some people were asking me about how this applies to multiply connected domains. So I thought I'd illustrate it here. So here we have a triply connected domain, which is the region that's outside all three of these figures. It was easier to draw a grid of points on the whole thing and not worry about whether they're inside and outside, since the map works anyways on inside and outside. The irregularity there is just problems with PostScript putting points exactly where you tell them to put it. So the points are actually fixed. So the idea goes back to Kirby, which says the following. Take one of these figures like this star and look at its complement in the Riemann sphere that's simply connected. You map that to the complement of the disk. And so when you do that, this is the new region that you get. So you can see these light points here correspond to the tips, which have very large harmonic measure, and the dark points correspond to the gaps between the tips, which are relatively hard to get. The map is normalized to look like Z plus O of 1 over Z infinity translation. The inside, well, I forgot to normalize the inside, so at similar rotation, you can see where the tips and the inward pointing and outward pointing channels are. The point is, look, this anchor looks exactly like what it looked like before. There isn't any difference. And even this boomerang, you haven't even begun to, you just barely influenced it right here. This map is very close to a linear map outside, just a little bit away from the disk. That's what happens with these slit maps. You take these little slits and map them to a vertical slit to a horizontal slit, or a horizontal slit with a bend. Once you're just a couple times the length away, the map looks very much like the identity. Now Kirby's idea is to repeat this only using now the next region. So we map the complement of the boomerang to the complement of a disk and normalize it to look like Z near infinity. And this is the region you get. Notice that the image of the circle, it's not going to be a circle, but it's really close to a circle at this stage. Very close to a circle. And the anchor still looks like an anchor. And now we repeat it again with the complement of the anchor, and we get three regions. The green one is a circle, and the other two are fairly close. In fact, even at this stage, visually, it was impossible to see. I had to take out transparency and try to rotate it around the surface to see visually. So Kirby's idea is to continue repeating, touch each one infinitely many times, and that will converge to the conformal map to the point. So this is to create all these pictures took 35 seconds. Boundary most of the time was spent reading and writing the files. So it's fairly quick.
This famous server problem still open for architecture?
Yes, it is. What do I think?
This says it's true.
I believe that that's right. How many circles and the rest of the points. The difficulty with that problem is you can't set it up as an extreme problem. Even this one, right? So a way to understand this is maps by vertical and horizontal slits can be set up as an extremal problem, kind of like what I wrote down before, maximizing the real part of the grid, horizontal and vertical slits. This one, there isn't any extremal problem for which this is a slit. We did.
So I like this one. My contribution to this was formulated something called the generalized Kirby conjecture, which would apply the regular one. It has more topological flavor. I'll tell you about this. So, Simpson solved that one. We have another backup question waiting.
I guess we didn't mention this to everybody. So the problem is you have an infinitely connected domain, and you map it to a region bounded by circles, where you allow some circles to have zero ranges, points in circles. If you have, say, a complement of components, that's known.
So things are like the outsides of Cantor sets and things, that's where.
So any domain, kind of said, applies to any domain. Same applies to any domain.
Yeah.
Any connected.
Only connected.
Connected. That's it.
Questions? Well, I had a question, although actually be for Toby, because I should have asked him in his talk, but either one of you can answer it. These multiply connected domains. I mean, Toby had told me that the next big problem in conformal mapping was the multiply connected case. It wasn't quite clear to me what was the acceptable answer, like mapping onto a domain bounded by circles, as the canonical domain might be, or maybe mapping on the slits, or I tend to think of mapping as a covering map, so maybe like the covering infinite, the one covering map from the disk would be your answer. But why? If you have a Jordan domain, you could say, well, if I can map conformally to the disk, there's an explicit formula for the Poisson integral, I can solve a Dirichlet problem and transfer it back. But if I have a domain bounded by 5 polygons, and I map it to something bounded by 5 circles, I still don't have an explicit formula for solving the Dirichlet problem, the Neumann problem, or anything. What advantage have I gained by mapping it to a canonical domain?
Well, I was at a talk, Dyer, I think, was saying, you know, the typical problem we still refer to about doing airflow over a wing using conformal mapping methods. Well, he said it's actually not a cross-section that's a simply connected piece. There's actually the wing, a separate flap, and then I think another piece. So it's typically a 3-connected domain. So if you can map it to vertical slits, you can do the same thing. The airflow in the vertical slits is straight, and the conformal map carries that to the airflow around the 3 actual shapes.
Okay, so there's...
You have to introduce lit. If you want to do the map to the complement of that region, you don't map to the complement of a slit. You map to the complement of a slit to one gap. And that gap is related to the lit.
Oh.
Read off from the real part.
Oh, didn't know.
Still short stuff.
But do you have other examples where if you map a multiple connected domains to some more canonical shape, you have a problem that's easier to solve and then transfer back to the original
I think I can solve a boundary value problem by mapping each component to a specified real code. Give you another example.
For doubly connected domains, you can write things down.
Yes.
So that would be one.
In my mind, that's because the covering group is just linear growth, Z, and then when you have many components, you keep going around loops in exponentially many different ways.
One other possibility is that if you have a triply connected region, like, say, a part of the brain with 3 pieces removed, and you wanted some numbers to attach to it, you could conformally map it to something where you can read off the numbers associated with the moduli sort of that. Like if you put it
Well,
in...
again, if you map it to some rectangular slit domain, it's easier to compute extremal length, I guess.
Yeah, well, extreme length is one case, and you can have multiple connected domains where you have more parameters that specify the conformal type of the domain.
The philosophy really for conformal mapping is that you start out with a complicated partial differential equation on a complicated region. If you make the boundary much nicer, so you can simply map to a circle or
So you're
whatever.
use like finite elements and a grid method. It's smoother boundary would be better than...
Smoother boundary would be better, and hopefully, and usually, maybe your differential equation is not much more complicated on the new one. Well, Laplace transfers easily, but other ones, they're not identical, but hopefully not too much
Okay,
worse.
that's sensible.
And so then just this idea of mapping to a region bounded by 3 nice analytic curves
Right.
might be a good.
Well, that
So
doesn't
you could
happen.
represent there's a Fourier series of these curves much more easily.
Okay.
In the convergence of this algorithm, this new result, you can't prove it by just showing that this is going to converge to a Loebner equation, to the solution of the Loebner equation.
No. I don't.
I mean, just by subdividing more and more finely, and I don't know. It's a discrete procedure. It's
The
several
problem
other
is
methods
both
on
the Loebner and this are, in a sense, repeated composition. This does
Yes.
give the solution of Loebner's equation. I mean, it's exactly showing, you watch where a point goes, and that's exactly the parameter in Loebner's equation. But the problem is you have repeated compositions, and so you can't trace the estimates through repeated compositions to see what happens at the end. That's always the difficulty. You know things go for a finite number of iterations, you know how things wiggle. But what happens after many compositions is very difficult to estimate.
I mean, so I'm just saying, can you go to an Euler type method for solving the Loebner equation and then get your algorithm out as a discrete way of integrating it.
Something more like Picard, where you
Well, it's sort of like Euler, where map composition is the operation instead of just addition. Differences.
Right.
So Euler sort of in his